It doesn't take a trained ear to know when something sounds off in music. A wrong chord, a misplaced beat. Even a single note can cause a reaction. What most people don't realize is that the reason that we recognize these errors so instinctively is because music, at its most fundamental level, is math. And that's not metaphorically, that's literally. Before there were pianos, before there were staffs or notes or even the word music, there were strings. In ancient Greece, around 500 BC, a philosopher named Pythagoras did something deceptively simple. He stretched a string tight and plucked it. Then he divided the string in half and plucked it again. The second note was exactly 1 octave above the first. That wasn't just sound, it was ratio, 1 to 2. He went further. Divide a string into 2/3 ratio, and you get a perfect fifth. In 3/4, a perfect fourth. These simple mathematical relationships became the foundation of Western music. Harmony wasn't an accident. It was math aligning with human perception. And over time, this evolved into what's called the diatonic scale. 7 notes that repeat in octaves. Every familiar melody in Western music, from Mozart to Motown, operates within this framework. But here's where it gets really interesting. The math never really stops. Take a rhythm, a 4/4 time signature. It means each measure is divided into 4 beats, otherwise known as quarter notes. A 3/4 signature, that's a waltz. The division of time into fractions like 1/8 notes or 16th notes is pure subdivision, just like fractions on a ruler. Polyrhythm, syncopation, swing, they're all variations on dividing and emphasizing beats with mathematical precision. Even tuning itself has a very hidden battle behind it. The equal temperament tuning system, adopted widely by the 18th century, it's ultimately a compromise. It slightly adjusted the mathematically perfect intervals to make all keys usable across the keyboard. And do you know why? Because the exact harmonic ratios Pythagoras loved didn't fit neatly across 12 notes per octave. The math broke down. So we fudged it just a little bit, and that made the music work. The compromise affects every single piano, guitar, and orchestral instrument today. When you hear a beautiful sonata or a rock solo, you're not hearing perfection. What you're hearing is a system of deliberate imperfection designed to make all keys equally usable. It's a trade-off. It's a trade-off that lets a composer switch from C major to B flat minor without retuning the instrument. Is it useful? Absolutely. Is it pure? No, not quite. But the story doesn't stop with instruments. Digital music, compressed audio, auto-tune, all of it is built on algorithms and signal processing. The tones that you stream through your headphones, they're not waves, they're samples. Typically 44,100 samples per second. Each slice of sound is represented by a number, and then compressed using logarithmic equations that preserve the sound while shrinking the file, just like this audio that you're listening to today. It's no exaggeration to say that every note that you've ever heard, whether it's from a violin or a streaming device, at some point, the ratios are reduced. Frequencies, patterns, and divisions, it's all reduced to these core elements. And yet somehow it still moves us. The math explains the structure, but it does not explain the soul. And maybe that's the secret. Music feels timeless because it bridges something cold and logical, numbers, with something entirely human, emotions. You can write an equation to describe harmony, but you can't write one to explain why a certain chord change gives someone chills. Well, not yet anyway. The next time you hear a song and tap your foot without thinking, consider this. Your brain is doing real-time calculus. You're decoding subdivisions, recognizing symmetry, detecting pattern breaks, all without knowing a formula. It's not just appreciation. It's mathematical computation. And whether you're aware of it or not, you've been fluent in musical mathematics your entire life. These are Interesting Things with JC.